Hello, my name is Zeynep. Today I'll be talking about my Physics 212 project, which is about relativistic effect on energy on momentum of beta particles. So beta particles are just basically really fast-moving electrons ejected from radioactive decay. So naturally you expect some relativistic effect on it. To test and confirm that that is the case, we looked at the most basic case that we can look at, which is the charged particle moving in a uniform magnetic field case. So basically, classically, we already know what's going to happen. You have a charged particle in a uniform magnetic field. It's going to have a Lorentz force of QV cross B. If V and B are orthogonal to each other, that's simply going to give you QVB. And then from there, you're going to equate that to the centripetal force, which will give you R max equal to mv over qb. Equating mv to p, linear momentum, and then writing that in terms of kinetic energy, you get R maximum equals to the square root of 2mq over qb. Now, the reason we write it in terms of q, the kinetic energy, is because that q is actually the decay energy of the radioactive source that you picked. So what ends up happening is that the source's decay energy completely goes to the kinetic energy of beta particles. So you know for each decay what the beta particle's kinetic energy is going to be. It's going to be that constant Q value, so it's easy to deal with. And for our case, we had strontium-90, so it was 546 kilo electron volts. And for the relativistic case, now we again have P over QB, but this time P needs to be modified to gamma mv. But again, we don't want to work with those. Instead, we use Einstein's formula, relating energy to momentum, and then simply after writing energy in terms of kinetic energy plus initial energy, rest energy, we get the formula for the relativistic case for R max. And basically, from this point on, we need the magnetic field. And the way we found magnetic field is that we basically stacked 2 to 3 magnets on top of each other, had a 5 millimeter separation, used the Gauss meter to find how big the value is going to be at each point. We plotted them. It wasn't, uniform enough and even big enough for that case, but we took it as uniform, which gave us error, of course. So we took it as 84 milliteslas with the error percentage from the Gauss meter, and then we found the values theoretically. From there on, what we did is that we basically went on measuring what the R max is actually going to be. So for this, after finding strontium-90 and after getting the magnets, we made a housing so that we wouldn't have any unwanted radiation coming into the system to be touching the jam tube. So we made a DIY kit jam tube. It was Arduino compatible so that we can log in the data that it takes, and later on, we put the magnets into the housing. It had 5 millimeter separation, and then we added a steel collimator to the source. The reason the reason this happens is because if you didn't put a steel collimator, first of all, it would spread around a lot, which we don't want. We want a region that we can clearly say this is where it's hitting, so these are the radius values, so after this there's no more. That means that's our maximum. The latest case where we got something notable is the maximum we can go. So because of this, and because of also the fact that you can geometrically find radius easily with the steel collimator. The reason is that within the steel collimator, the scattered beta particles will not be having any force applied onto them. But the moment they get out and they start their cyclic motions, the inner line that they were going on previously to the motion is going to be tangential. And we know that if a line is tangential to a circle from the radial axis, if you draw the lines, connect them, you get a 90 degrees. And that 90 degrees is good because that means that if we have an angle facing the inner radius and then also has a tangent of r over l, l being the length of the steel collimator, you can drag that theta angle by geometric interpretation and then say that that's going to be the same angle between the lateral distance of the circular motion and then your diameter of the circular motion. So even if your magnets are not able to keep the beta particle all the way through its motion that it goes to its 2r location, you can still, by simply looking at the lateral distance and using the geometric fact, get what 2r is going to be, and then from there you're going to get what r max is going to be. So all we needed to do is find lateral distance maximum value, and what we did is simple. We looked at what background count would be on a regular basis, and then we basically calculated what the counts per minute, counts per hour is for every centimeter increment, and then we basically looked at when there's a clear drop from a high place. So what that means is that at a high place where the counts per hour is high compared to background, is that means beta particles are hitting there, but after the moment it drops, it means that they're no longer being able to pass to a region more than that, and that means d max, the lateral maximum distance, has to be somewhere in between that low and high point. So for our case, the last high data point was 8 centimeters, and from there 9 centimeters was low, so maximum lateral distance had to be somewhere 8 to 9, so we said 8.5 plus minus 0.5, and after doing the geometrical interpretation, we got R max to be basically 4.15. We also had a steel collimator on the jam tube and even an aluminum plate that had a slit on it, which also gave us a plus minus effect. So adding that two, we had 4.15 plus minus 0.25 as a result. And in terms of result analysis, that's too huge compared to both of the theoretical results, but taking into account the fact that the magnetic field wasn't uniform, the fact that it was overestimated likely, even that if it were to be a 10% overestimation, that significantly would change the result and would actually make it come closer to the result of the relativistic theoretical case. And other than that, another issue is the fact that the increments were too much separated. I mean, plus minus 0.25 is still a huge number compared to the fact that that change is actually quite considerable in how much they fit to each other. So if the increments were smaller, let's say 2 millimeters to 2 millimeters, and we found it to be between 8 to 8.2, then our result would be way closer to the theoretical case. Finally, we can say that regardless of the errors, no matter how much we increase the precision, the fact is that the value would be likely to come closer to the relativistic theoretical output and no further to the classical case. The classical value is so small compared to both of the other results that it is unlikely to explain what's going on for this motion, therefore proving that there's at least some definite relativistic effect happening onto the beta particle. So our project agrees with the already well-established predictions of special relativity, further proving its claims to be true for the case of cyclic motion of beta particles. And that's our project. Thank you for listening.